Hi guys, my name is Suyan Betty Huang, and this is going to be a 15-minute video clip about quadratic function and its graph. This is actually the very first video that I'll be recording, so I hope you guys enjoy this video and learn something important about quadratic function. So here we go. So quadratic function. What is quadratic function? I'm sure you've heard of this quadratic formula, quadratic equation, and all this word oftentimes. But what actually is it? So it exists in many different forms, but first we're going to be talking about the standard form. So this is how the equation of the quadratic function will look like. As you know, you should be all familiar with the linear form, which is often written as y equals mx plus b. So this is linear function, linear equation, whereas this y equals ax squared plus bx plus c is a quadratic function, and it's very standard form. So notice that in our linear form, we have x. It doesn't have any power, it's just mx. But notice in our quadratic function, the order of the highest x term is actually second power. So that's that's how you can actually tell the difference between a quadratic function and a linear function. So if it's linear, then you only see x, and if it's quadratic, you will see some kind of x squared. So this is quadratic because it has x squared. And a and b and c, these are going to be just numbers. We are representing as a and b and c as random variable, but when we write it in our problems, we should have actual numbers, whether negative or positive, in front of x squared and x and c. Yeah. But another important thing is, sorry, I just wrote a lot all over the place. This a cannot be 0. It cannot be 0 because if it's 0, then this whole term is going to disappear, and it's just going to look like bx plus c, which will actually end up being a linear function. So it's just really important to notice that a cannot be 0. It could be negative, it could be positive, but it just cannot be 0. Let me just write it down so you will remember. Just a cannot be 0. Yeah. Alright. Next. So the graph. So how does the graph of a quadratic function look like? So I'm sure on the linear function, I'm sure you've all seen some kind of line like this. This is linear because it is a line. This is linear. But our quadratic function, our graph will look like this. And we have a special name for this U-shaped graph. Yes, U-shaped figure. We call it a parabola. Parabola. So it looks like a U. It's not line. Even though this part kind of looks like a line, it's a curve. It's a curve. It's a very smooth curve. It's all continuous everywhere. But yeah, it's a U-shaped. And what is so special about this parabola? What is so special? So we're going to talk about this. So there's a definition of a parabola, which in mathematical world we call so this is defined as a set of points that are equidistant from a fixed point or a focus and a fixed line or a directrix. So equidistant means it's just like the distance is equal. Okay, let me just explain it clearly or rephrase this mathematical definition in our very own word. So we have, when they mean by set of points, they're saying, oh, if you look at closely enough of this graph, it's actually consisted of lots of points. But because there's so many points, it just looks like a line. So it's a set of points that are equidistant from a fixed point. So suppose I have this point over here, right? This point is the distance between, I'm gonna call it the distance what? D1. Here, this is a distance from a point over here, and another distance, I'm gonna call it a D2. The point from this line this line to that point, and distance from this the same point on our graph to this point called focus, they're equidistant. So meaning this distance will be equal to this distance. So okay, let's pick this point over here. Oops, that point is a little ugly. Okay, so I have another point on this graph over here, and if I draw a line from this fixed point, so when they mean by fixed, it's just there. We're never gonna change it. It's fixed. We can never change it. So distance from this focus point, a fixed point, I'm gonna draw a line, straight line, and if I just drop a perpendicular line to this line called the directrix, the distance will be the same again. So it's once again a set of points that are equidistant from a fixed point, which is focus, and a fixed line called a directrix. So this is very special feature of a parabola. So we just talked about the standard form of a quadratic function, which we write it as y equals ax squared plus bx plus c. So our parabola is a U-shaped, but it could exist in either open up, our regular U that we are familiar with, or it could open downward. So how can we tell whether our parabola will look like a U open up or open down? Well, it's all up to the number that we'll be having in front of x squared. We usually call it a. So you remember we talked about how our a cannot be 0. So suppose it cannot be 0, meaning that now a could be either a positive number or negative number. So negative number and a positive number. So if I have a standard form of a quadratic function, y equals 3x squared plus 2x plus 5, whatever, I could say, oh, this is going to be an open up. Why? Because the number in front of x squared is a positive number. Whereas, okay, what if instead of 3x squared, what if I have negative 3x squared? Well, then we know, because it's a negative number in front of x squared, it will be a downward parabola. So notice we don't really care about the values that are in front of x and just the number. For the sake of either the parabola is facing up or facing down, we are only concerned about the number that's in front of x squared. So yeah, this parabola is such a negative, very negative, then that's really sad. So I make a sad face. Sad, because this parabola is so negative. By the way, this parabola is so positive, very, very happy. I don't know, that's just how I remember it. I have drawing everywhere. But just remember that when it's negative, then it's facing downward. When it's positive, then it's facing upward. Yeah. So I do have a typo here. I put x-axis, but this actually should be x-intercept. Just going to type over here, x-intercept. So just disregard what I put over here. Shouldn't be x-axis. Alright, so yes, we still have our parabola here, and we're going to be talking about some of the clues that our parabola gives to solve our future problems. So we have our standard form over here, y equals ax squared plus bx plus c once again. And just remember, a, b, c could be any number. Our number, they're numbers. They're numbers. So there's a very special character about parabola, because it's a U-shaped, it could cut into half right here, and we call the line of symmetry. Why? Because when it cuts into half, meaning this side and this side has like the same area. Just like when you cut the square into half, because they're symmetrical. Okay, it doesn't really look like a square over there, but because it's when you cut into half, this area are the same because they're symmetric. Just like the same concept, our parabola could cut into exact half, where they're going to have like the same distance from here to here, here to here. So we call it a line of symmetry because they are symmetrical. And there's a way for us to figure out where the line of symmetry is located. So we can figure out where the line of symmetry is, and our equation is given right here. How wonderful. So how do we figure out the line of symmetry? We use this equation, x equals negative b over 2a. So once again, the b value is from the equation over here, and a value is over here. So I'm going to just give a very quick example in a moment after this slide. Yeah, after the slide though. But yeah, just notice that we could find the line of symmetry using this equation. X equals negative b over 2a. Sorry about another typo. This should be x-intercept. I don't know what I was thinking when I was making the PowerPoint. But yes. Alright, here we go. So I actually have x-intercept instead of x-axis like last time. So x-intercepts are also called the solutions because when we try to find a solution of a problem, and if the problem context is if the problem could be written in a quadratic function, then what we are actually doing is we're looking for the x-intercepts, and then these are the solutions to the problem. So it'll be a lot more clear when we actually have a problem. But as of now, we also just know that we call x-intercept as also the solution of a problem.